Good morning, everyone. Welcome to IME 470 class. Today is April the 3rd, and today we're going to continue the lecture in dynamic programming. And let me first stop the video here. And okay, so I assume you can see my screen, right? Because let me see. I think I've already shared. Yes, I've already shared the screen. Let's continue the topic. So in the last topic, we mentioned, let me take this one out. In the last lecture, we mentioned the dynamic programming. And here I introduced the two games, okay? And the main idea is that the characteristics of the DP are first, a problem can be divided into different stages. And the second thing is that we can find a recursive relationship. This recursive relationship is something that the solution to the next stage only depends on the solution to the current stage. This is also called the principle of optimality of DP. And let's continue the introduction of the shortest path. Today, let's do a little bit more. First of all, I do need to review this one. This is extremely important, that in order to get the shortest distance from S to T, I only need to get the shortest distance from S to 2 and to 3 and to 4 and to 6. Why? Because from which node you can get to T, you have only 4 cases. In other words, as long as I know the shortest distance from S to 2, from S to 3, from S to 4, from S to 6, I only need to do this. That take the minimum of the shortest distances to here. Here, ij is in A means, give me 1 second. Okay, so here we are gonna calculate the ft, right? This is j equals to t. So here it is in A means I can go from node I to node t, and this j or t is fixed, but this I is, the incoming nodes. So this formulation in this graph, when j equals to t, means the minimization of f2 plus 19, comma, f3 plus 6, comma, f4 plus 16, comma, f6 plus 44. Okay, and I want to get a minimum. Of course, by logic, it's very easy to verify that as long as I get the minimum of this, I can get the shortest distance from S to T. Then the question is, how would you get to 2? I mean, from the shortest distance from S to 2. Similar, from which nodes can you get to 2? I can go from node 1 or node 5 or node 3, right? So here, this formulation becomes what? Becomes j equals to 2, so that you have I as a selection from the set that I2 is in A. So this means the I are 1 or 5 or 3. And then you're going to calculate, for example, f1 plus 24, comma, f5, the minimization of them, f5 plus 18, comma, f3 plus 6. And then you're going to choose the minimum. And then again, you can do the same. And until you reach to, for example, f1. f1 must be equal to 9, sorry. Why? Because only S can go to, from only S you can go to node 1. f5, similar. f5 must be equal to 11, because you can go from only S to 5. However, be careful about 6. Actually, f6 is this path. Here, I'm kind of like cheating. I directly tell you the solution, okay, which is 16. Rather than you directly go from S to 6. From S to 6, you get 17. So, and later today's lecture, we're gonna have a introduction, which is a systematic way how to do this step by step. So theoretically, for any given graph, no matter how complicated it is, you can use this method, which is the Dijkstra's algorithm, to solve the shortest path. Okay, so let's continue. First of all, something like notations. Again, the recursive formula is this. This and this are the same. I just copy and paste. Okay, and let me draw a box here, because this is extremely important. This is the key of everything, actually. And then in terms of the calculation, we're going to get the fj's forward. Why? Because we're going to start from S and then S1, S5, something like this way. But when we are thinking about the problem, we're going to think of the problem backward. For example, from T, then I'm going to go this level, and then I'm going to go this level. This is actually what? Exactly the same as these problems. Remember, as these two games. This game, if I want to count to 20, I'm going to think backward. That in order to get 20, I only need to get 17. To get 17, I only need to get 14 backward. But when I'm thinking about it, I'm going to think forward. Why? Because I'm going to get, 20 divided by 3 equal to 3 plus 2, right? The 2 is the remainder. So that I'm going to say, I'm going to get 2 first, and then 2 plus 3 equals to 5, 5 plus 3 equals to 8, blah, blah, blah. When I'm calculating, I'm going to calculate forward. Similar here. I'm talking about the first method, okay? Similar here, if I want to know the total number from 0, 0 to 24, what I only need to do is that I need to know what? I need to know the number. I need to know the number from 0, 0 to 14 and from 0, 0 to 23. And then, I do this way, and then I'm thinking backward. But when I'm calculating, I'm going to calculate forward. Why? Because you have to start from 0, 1, 0 and 0, 1 first, because you exactly know that's their 1. And then what you need to do is to take advantage of the recursive formula, which you got actually backward, and then use the forward way to calculate them. So this is the point of the DP algorithm. And you must have these two principles. That first, you have the problem can be divided into stages. By stages, what I mean is actually discrete stages. And number two is that you do have a recursive relationship. Otherwise, this backward forward way doesn't work. Okay. Now let's see some more definitions about the Dijkstra algorithms, the Dijkstra algorithm itself. Because here a problem is, I mentioned that when you are thinking, you're going to go backward, but when you are calculating, you're going to go forward. Then there's a contradiction. So what is the correct order? I mean, say from this level, we know it is 2, 3, 4, 6. And then from this level, from 2, I know 1 and 5. And then, from, let's say, 5, I know S. Good. From 6, I also know 5. And then I also know S. Then from 4, I need to know 5 and 6 and 2. How about 3? From 3 and 2, know 4. The question is, 3 is going to directly contribute to 2. Then the problem, what is the order? Should 3 be considered before when we're talking about 2, or should 3 be considered after when we're talking about 4? You know what I mean? What is the correct order for you to calculate or to get the shortest distance from S to node I, which I is any, this kind of nodes, any nodes here except for S itself. Then that's a problem. So Dijkstra's algorithm actually systematically solves this issue. First of all, in Dijkstra's algorithm for the shortest path problem, SPP, we have two types of nodes. Nodes with fixed distance. Let me draw a line. Nodes with fixed distance from S, of course, and also nodes with temporary distance. Fixed distance means that the distance is already, fixed. It's permanent. And temporary distance, that it's temporary, we can update them later. And actually, the Dijkstra's algorithm, the whole step that the whole algorithm that we're doing are only 2 steps, which is to fix a node and then temporary find the next node to set up the temporary distance, and then fix a node temporary setting distance like this one. So basically, we're updating temporary distance by new added fixed nodes and make the temporary nodes with the minimum distance to the new fixed node. Let's have a look. Before doing so, let me again make the notations very clear. First, V is a vertex set. So for example here, the V equals to ST and 1, 2, 3, 4, 5, 6. That's it. Which nodes are there? It is going to be inside the V. And the A, as we mentioned before, it is the arc set. In other words, if there's a link from A to B, then AB will be parentheses. AB will be there. For example, here we have totally 15 links, so that A is just a set to record all these 15. links. For example, you can see phi 2 must be inside. Phi 2 is here. 1 2 must be inside. 1 2 is here. As long as there exists a direct link, then it's going to be inside. For example, S4 won't be there. You cannot find S4 there, right? Why? Because there's no direct link from S to 4. And this is A, the arc set. Wij, as we mentioned, is the weight or the direct distance from I to J. Be careful, here's the direct distance. For example, you don't have S to 6 equals to 16. Rather, you have S to 6 equals to 17 because it's a direct distance. 16 because you go from S to 5, 5 to 6. It's not a direct, okay? And if, for example, I don't have a direct distance, for example, suppose I want to ask, what is WS to 4, WS4? Then, oh, okay, here I wrote W14. What is 14? It's infinitive. Why? Because there's no direct link from S to from 1 to 4. And then the next one is f function. Actually, f vector. F vector is defined by the record of all the shortest distance from S to the current to whatever node 1, 2, 3, 4, 5, 6, and T. It just contains the distance from S to all nodes. And then one very, very important thing is this. This is the out neighbor notation. So for a fixed I, when we write Ni, that means I is fixed. Then J is in Ni means Ij is in A. That means what? That means J from I, you can reach J. Okay. So for example, we can have a look. Let's say what is N5? That is equivalent to ask you from 5 I can get to which nodes. So clearly from 5 I can get to 2 and 4 and 6. So that N5 equal to 2, 4, 6. Another example, for example, 4. What is N4? From 4 I can reach 3 and T. That's it, right? Yes. So that you have N4 equal to 3T. Okay. In conclusion, again, Ni means the out neighbors. No, the out neighbor nodes that node I can reach. Okay, now we can have a look. Oh, two more. Sorry. The next one is Fn set, which is to record the set of fixed nodes. Remember here we classify all nodes to be two types. First is fixed distance and nodes with fixed distance from S, and nodes with temporary distance from S. So Fn is to record the nodes from fixed node, the nodes from the nodes of fixed distance from S. Okay, and then clearly, if a node is not in Fn, is not fixed, then the node distance to S is temporary, and we use Pi to record the path from node S to node I. It doesn't matter this I is fixed or not, and we will see later. So this is a summary of Dijkstra's algorithm. Here, I'm gonna briefly mention it. Again, I think we directly start from examples. It's gonna be easier for you to understand it. So first, step 0, we need to do an initialization. Then in step 1, we're gonna update out neighbor's temporary distance by this recursive formula. And then step 2, we're gonna fix a node which node to be fixed, we're going to choose the one with the minimum temporary distance. And then we're going to just simply repeat step 1, 2, 1, 2, 1, 2. You're going to see a lot of repetitions in this example. And finally, optimality test that as long as T is fixed, I'm done. That's it. 2 remarks is that once a node is fixed, it's permanently fixed. We will never, ever try to update it again. And the second thing is S and T are also 2 nodes. Okay, let's directly go to the example. And after many times of repetition, you're gonna know what does step 1 and 2 really mean. Okay, so first, this is a graph, the same graph I can just copy and paste from the previous example. And now the initialization step tells you that Fs equal to 0. Again, what does Fi mean? If I is a node, then Fi means the shortest distance from S to node I, right? So what is the shortest distance from node S to node S itself? Of course, it's 0, And then we temporarily set Fj equals to infinity. So this J is for any other nodes. Other means any nodes except for node S itself. So that here J is 1, 2, 3, 4, 5, 6, and T. Okay, and then we set we put S into Fn. Again, Fn, what is Fn? The set of fixed node. That means, okay, we have fixed the distance from S to S, of course. S to S itself is 0. So that here we have Fs equals to 0 and Fn, the set of fixed node, is S itself. And the Pj is itself. From S, I go from S to S directly. And all other paths are empty set. This means empty set. Or you can definitely write, empty set here, but I'm kind of lazy. So we can just simply leave it blank. That's very simple, okay? So now we have this table. And in the whole example, we can update this table. And meanwhile, I'm going to show you this graph. So it's going to be 1-to-1. You're going to see it the step by step, very, very clear. Okay, and now this is the table. This green color means it's the most recent added point. And you can see here, I actually have a 0 star, okay? So here are two factors. Factor number one is that I use the green point, a green font for what? For this FS. The reason it is green because I want to show that this is the most recent added or most recent fixed node. And the reason I put a star here, that means it's a permanent. Whenever you see a star, that means the node is permanently fixed, so that we will never ever try to update the distance. Okay, now let's go to step number 1, which is updating neighbors' temporary distances. Okay, you're gonna find the most recent added node, which again I use the green color, and then you're gonna try to find its all out neighbors. Again, out neighbor means for example, from node S, which node I can go to. Okay, from node S, I can go to 1 or 5 or 6, right? Okay, very good. Then use this recursive formula. You're gonna do this. Okay, what is F1? F1 means the previous F1, where it is. Okay, this is something not very good because I need to have a look at this table. So the previous F1 is what? Infinitive, right? Okay, now you're gonna have F1 as from the previous F1, which one is minimum, or from S to this F1. From S to F1, this one is from S to S, which is 0. From S to 1 directly is 9. So you're going to compare the minimization of infinitive versus 9. Of course, it is 9. So when the path is updated, you're going to go to the new path. The new path is what? The path from S to the most recent added node, which is from S to S. Then from this S to 1. So 1 means node 1. So that the path is going to be S and 1. This P1 means what is the current, be careful, current, it's not fixed, okay? It's temporarily. What is the current shortest path from S to 1? And this tells you, okay, the current shortest path from S to 1 is from S to 1. That's it. Okay, let's have a look at node 5, similar. In the previous table, node 5, the distance is infinitive. See here? Okay, now use this recursive formula, you're going to compare which one is shorter. The previous distance, which is infinitive, or the new distance, which is from the most recent added node, which is S, to this node, which is 5. So that you have S to 5 equals to S to S, which is 0, plus directly from S to 5, which is 11. This, of course, equals to 11. It's updated. Updated means it's no longer infinitive. It's updated to 11. So this means your new path 5 equals to the path from S to the most recent added node, which is S. Then from this S to 5. So that your S P5 equals to S to 5. And you're going to do the same for node 6. Node 6 equal to, again, here, infinitive. From infinitive to go from S to 6. And it equals to 17. So again, your temporary shortest path currently is from S to 6, okay? And the second step, what we're going to do is we're going to fix a node. So fixing a node, so at, excuse me. So at here you have this table, okay? So I already updated all the F. So Fs equal to 0, And you have F1 is updated to 9, F5 is updated to 11, and F6 is updated to 17. And correspondingly, you update all these PJs. Again, empty means empty set. Empty set. Blank means empty set. Okay, now the second step, you're going to fix a node. By fixing a node, what I mean is that among all these temporary distances, temporary, okay, here, these are temporary. Come on, get out. No, I don't need a text. I need this. So this is temporary, 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 temporary. As long as you don't see a star here, it's temporary. You see a star here, it's a fixed. Once fixed, permanently fixed. Okay, among these temporary nodes, you want to find a node which has the smallest distance. So very clear, if here I want to have the smallest distance, it's clearly this number, right? Okay, then I'm going to fix this node. And here you can see, I'm going to fix 9. Again, use this green color, I mean, it's the most recent fixed or the most recent added node to the set Fn, fixed node set. Okay, and corresponding in the graph, you can see. So in the beginning, I fixed S. I use the red color to indicate fixed and use the green color to indicate most recently fixed. Okay, so from S, then in this step here, I fixed 1, and I use again green color to indicate this is just fixed, most recent fixed. Okay, now my most recent added node becomes 9. What to do? Again, step 1, updating neighbors' temporary distances. This time, which one? Oops. This time, which one will we check? We're gonna check where it is. I really hate this. It's very unstable. It's always too sensitive. Very easy to jump automatically. Okay, here's slide 17. Okay, we're gonna fix the node which is 9. Very correct. Okay, and then we're gonna do the temporary optimality test, which is clearly T is not fixed. So we go to step 1, which is again to update neighbor's temporary distance. But which one should we consider this time? You're gonna always consider the most recent added node to Fn. Which one? The green one, right? Which is node 1 here. Okay, so again, you're gonna ask yourself, from node 1, which node can you reach? I can reach only node 2. So easy, update node 2. In the previous table, node 2 is what? Is infinitive. Okay, so that you have F2 equal to the previous distance, which is infinitive, versus the new distance. The new distance equals the most recent added node, the distance of the most recent added node, which is 9, plus 24. 24 is the direct distance from 1 to 2. Which one is smaller? Of course, it's 33. Okay, it's updated. Updated means it's no longer the previous minimum distance. So you need to update the path again. The path updated is, so what is the shortest path from S to 1? You find this table, oh, it's fixed to be S to 1. Good. So you just copy and paste this S to 1 plus a 2 here. So that the current shortest path from S to 2 is S1, 2. And the distance is updated to be 33. Okay, and then again, step number 2, you're gonna fix a node. How to fix a node? Simple. In this table, you're gonna ask yourself which temporary node has the shortest distance. Okay, again, temporary distance means there's no star. And clearly, among all these numbers, which one is the shortest number? Is the smallest number? Node 5, right? With 11. Good. So we're gonna fix node 5. Again, I use green color. Okay, all others I make it to be red to indicate that they're fixed. Okay, so here in the graph correspondingly, you have this. You have fixed S and 1, and you need to fix 5 at this time because 5, its distance, temporary distance is 11, which is the smallest one among the current all temporary distances. So you have this. And optimality test, is T fixed? No, T is not fixed. Go to step 1. Again, you're gonna update neighbors' temporary distances. See it? We are actually repeating these 2 steps, updating updating temporary distances, fixing a point. Updating temporary neighbors distances, fixing a point. See it? Okay, now let's come here. So my current most recent added node to Fn, or you can say the most recent fixed node is 11. Is node 5, whose distance is 11. So let's see, from node 5, which node can we get to? In other words, what are the out neighbors of 5? Clearly, from 5, I can go to 2 and 4 and 6, right? So I need to update 2 and 4 and 6. Okay, have a look at the node 2. What is the distance, the previous distance, shortest distance? To node 2 is 33, with the path S21 to 2, very clear. It's 33. Okay, so you're going to compare 33 with the new distance. The new distance is, you're going to go from 5 directly to node 2. So what is the distance from S to 5? It is 11, right? So you're going to have 11 here. What is the distance from 5 directly to go to 2? It is 18. So the new distance is going to be 11 plus 18. And clearly, 11 plus 18 equals to 29 is less than 33. So we're going to update the distance from S to 2 from 33 to 29. Okay? And because it's updated, it's no longer 33 anymore. So I'm going to update the distance. Update the path. So here, this means you're going to add the path from S to 5, and then to the new path 2 here, and then followed by a 2. What I mean is this. So you're going to ask, what is the path, shortest path from S to 5? From S to 5, we just fixed. It's from S to 5 itself. Then the shortest distance to 2 is S to 5 copy and paste, and then from 5 to 2. So that your current temporary path, shortest path from S to 2 is S to 5 to 2. And now is node number 4, the same. Minimization of the previous shortest distance from S. The previous shortest distance is infinitive. And the new shortest distance is the new distance. I cannot here claim it's the shortest. The new distance is from S to 5, which is 11, then from 5 directly, it's here. From 5 directly to 4, which is 30. So the minimum is 41. Again, because it's updated, so that you're going to update the path. The path here is, again, you copy and paste from S to 5, then from 5 to 4, so that the path here is S to 5 to 4 with the shortest distance, temporary shortest distance, 41. Okay, and for 6, similar. In the previous iteration, my shortest distance from S to 6 is 17, with the path S directly go to 6. Now, what I have is what? What I have is 17 versus from 5 to 6. Again, because 5 is the most recent fixed node. Okay, so 5 to 6 is 11. S to 5, the shortest distance fixed is 17. So, is 11. So that here from S to 6, the second route is 11 plus 5 equals to 16. And clearly 16 is smaller than 17. So I did update, I do need to update node 6, the shortest distance from S to 6. So again, you copy and paste from the route from the path from S to 5, and then add a 6 here, so that your new shortest path from S to 6 is S to 5 to 6. It's no longer directly from S to 6. Okay. Again, step number 2, fixing a node. How to fix a node? That is, among all these temporary distances, you're going to find what? You're going to find the smallest one, which is clearly this one, right? So you're going to make this one to be green and with a star here. Where? Updating. Okay, it's this slide. So you are going to fix node number 6. So here, you're going to fix node number 6. Okay, and then optimality test is T fixed? No, T is not fixed. Okay, go to the next step. Next iteration, which is again step number 1, updating the neighbor's temporary distance. Okay, then again, you're going to ask yourself, hey, from node 6, which node can I get to? Clearly, you can, from 6, you can go to node 4 and node T. So update these two. Node 4, in the previous iteration, it's 41. And in the new distance is from 6 to 4. From S to 6, we have known the distance is 16. From 6 to 4, the distance is 20. So the new distance is going to be 36. Then you're going to compare 41 versus 36. Clearly, 36 is smaller. In other words, yes, you do need to update your shortest path here. So it's going to be the shortest path from S to 6, then from 6 to 4. The shortest path from S to 6 is S56, you know it, and it's a fixed, permanently fixed. So you just need to add a 6. So you just need to add a 4 after it, S to 5 to 6 to 4. That's it. Here we go, the temporary shortest distance path from S to 4. Then how about the t? Similar. In the previous iteration, the t distance is infinitive. And here, I can go from 6 to t. What is the shortest distance from S to 6? It is 16. What is the distance, direct distance from from 6 to t? It's 44. So it is the new distance. It's going to be 16 plus 44 equal to 60, which is the minimum. So you have to update the t. Previously, lucky it's empty. So here you just copy and paste S to 5 to 6, which is the shortest path from S to 6. Then just add a t after it. So this is the new shortest path from S to t. And then what is the next step? Step 2, fixing a node. See it? How to fix a node? Okay, again, among all these temporary distances, you're going to find the smallest one. 1, 2, 3, 4. Only 4 nodes. Which one is the smallest one? 29. So we're going to fix 29. Fix node 2. So here we go. We fix node 2, and in the graph correspondingly, you see this one becomes green. Okay, and again, you're gonna ask yourself whether t is inside. T is not inside. Okay, continue. Again, you go to step number 1. I don't know which iterations already. 1, 2, 3, 4, 5. 4 iterations because S is iteration number 0. This is already 4 iterations. Okay, so in the new iteration, in the 5th iteration, you're gonna update neighbor's temporary distance. Okay. So you're going to ask yourself again, from 2, which node can I go to? From 2, I can go to node 4 and node t, right? So you need to update F4 and Ft. Let's have a look at F4 first. In the previous table, this is slide number 21. F4 equal to what? F4 equals to 41. Okay. And then the new path is going to be from, where it is here? Okay, it's here. Okay, slide number 24 is here. Okay, the new path is from 2 to 4. The shortest distance from S to 2 have been known to be 29. From 2 to 4 is 2. So the new path, the new distance is 31, versus the previous distance, shortest distance is 36. Which one is smaller? Clearly 31 is smaller. So you need to update the path of 4, which is you're going to copy and paste the previous shortest distance from S to 2, and follow and add a 4 here. So S to 5 to 2, and then to 4. Okay, this is the distance, the current shortest distance to 4, with the shortest path to 4, with the shortest distance 31. And then how about t? In the previous iteration, the shortest distance from S to t is 60. The new distance here is you go from S to 2 first, and then go from 2 to t, which is 29 plus 19 equal to 48. And the 48 is smaller than 60. So you update, which means the current shortest path is going to be from S to 2 first, which is this one, then from 2 to t, this one. Okay, and what is the next step? Again, fixing a node. Okay, so among all the temporary, nodes, here I only have 3 temporary nodes. Which one is the smallest one? Very clear. Node number 4 is the smallest one, right? Okay, so we are gonna fix node number 4. Fix it, as you can see here. It's node is green, red, and here I have the green distance here. Node number 4 is fixed, whose distance is 31. And you're gonna ask yourself, is t fixed? Unfortunately, t is still not fixed. Okay, continue. And then your most recent fixed node becomes node number 4. See it? Okay, then again, from node number 4, which node can you get to? I can go to node 3 and node T. Okay, you're gonna update, check these two. So from node 4 to 3 is first of all, let me see. Okay, in the previous iteration, the shortest distance of node 3 is infinitive. Great. It's how many steps already? 6 iterations. And the 3 was never touched. Great. And this time it's going to be touched. So the previous shortest distance is infinitive. The new distance is you're going to go to 4 first, which costs you which is 31, the shortest distance. Then directly go from 4 to 3, which is 11. So that 31 plus 11 equal to 42. And so that you need to update it. The new shortest distance to 3 is 42, with the corresponding path S25 to 4 to S25 to 2 to 4, and then from 4 to 3. Okay, so this is node 3. How about the node T? Node T in the previous table we know it is 48. Now in this table, it is 48 versus how about from 4 to T? 31 plus 16, right? 31 plus 16. Okay, just a little bit smaller, but still it's smaller. So it's a 47, which is smaller than 48. Then yes, you have to update this T, PT, which is you're gonna go from S to 4 first, which gives you S25 to 2 to 4, and then from 4 directly to T. So you have this S25 to 2 to 4 to T. Okay, and then what is the next step? Again, fixing a temporary distance with the smallest distance, which is clearly here, because here you have only 2 candidates. The first one is node 3, the second one is node T, and you're gonna fix this one. Okay, then I'm gonna go the next step, and you're gonna ask yourself, is T inside? Unfortunately, T is still not inside. Okay, the next step for sure, only T itself. It's going to be inside. So you need one more iteration, which is you're going to ask yourself, okay, good. So from three, which one can I go to? Okay, be very careful here. Clearly from 3, you can go to node 2 and node T, right? However, you will not update node 2. Why? Because 2 is fixed already. See it? Again, once a node is fixed, it's permanently fixed. Okay, you're only gonna have a look at outer neighbors, which is not fixed. So here from 3, there's only one node that is not fixed, which is node T. So you're gonna update node T only. And a node T in the previous iteration, we have what? We have the shortest distance is 47, right? In the new path, we're gonna have what? We're gonna first go to node 3, which is 42. 42 plus 6 is 48. Be careful. This time you have what? You have the new path is greater than the old path, the previous path. So in this case, you don't need to do anything, okay? In this case, you're gonna keep this 47 and keep this PT. Clear? Again, why keep this PT? Simply because you're not going to update it, because the previous path is better than the current one. So why should I update it, right? So you don't need to do anything. That's it. And in the next step, what you do, fix a node, right? Okay. Fortunately, the thing is that here, there's only one temporary distance, which is T. So of course, you have only one choice. You're going to fix T. And now you know ft equal to 47. And finally, you add a node to inside to the fixed node, the index set of fixed node. And you're going to ask yourself whether T is inside. Of course, you just added it. So of course, T is inside. So we're done. That means the shortest distance from S to T is 47 with the path S to 5 to 2 to 4 to T. And mission accomplished. Clear? I know this is very new to you. Let me repeat it again. This is important. Okay, so let's do it quick. So initially, we start with node S. Okay, so I make S, I fix S itself and denote the distance from S to S as 0, of course. And I fix S with a star, and S is the most recent fixed or the most recent added node to Fn, so that I use green color. In real operations, for suppose you're in your homework or on the exam, right? You don't need to use different color. What you need to do is just underline it. You know what I mean? Or you can simply box it. Whatever you like. So, or you can circle it. Just make a notation for yourself so that you know which one is the most recent added. You know what I mean? Otherwise, you may forget it. Trust me, you may forget it in the real operations. Okay, and then we're gonna do step number. This is initialization, and you're gonna do step number 1 because here clearly t is not inside. You're gonna step number 1, updating neighbor's temporary distance. So node number 0 is your most node number S is your most recent added or most recent fixed node. So you're gonna update its outer neighbors distances, which are node 1, 5, and 6, using this recursive formula. Oops, where it is? Using this recursive formula. Okay, and then this is nothing but you compare the previous shortest distance with the new shortest distance. The new shortest distance means from node S to the most recent added node, and then from this most recent added node to your target node. For example, the target nodes here are node 1, 5, and 6. So, and here you update it. If this number, the shortest distance, is updated from infinity, for example, here it's from infinity to 6, then you need to update the corresponding temporary shortest path, which is from node S to the most recent added node, then from this most recent added node to the target node. So here, the most recent added node is S. So S to S is S itself. Then from S to the target node, which is S to 1. And do the same for node 5 and 6. Then we fix the node. Among all temporary nodes, here by the smallest distance. Here the smallest distance is 9. So I'm gonna fix 9. Okay. Then after it, you're gonna do what? You're gonna do the optimality test. Here I fix a 9. That is whether t is inside. If t is inside, I'm done. If t is not inside, continue. Continue means the new by the new most recent added node, you're gonna ask yourself which is the out neighbors of the node. That means from this node, which node can you go to? I can go from where it is. It's here. I can go from node 1 to node 2. So you're gonna, it's here actually. You're gonna go update. Well, give me 1 second. Sorry, which slide it is? Okay, it's here. Whew, I really hate the slide, just the jump itself. Then you can go from node 1 to node 2, and then you need to update node 2, which is again the same, the previous one versus the new one. And it's updated, so update the path. And then what you do, fixing a node. Okay, among all these temporary nodes, which one the smallest one? Node number 5. Fix node number 5. And then optimality test, t is not inside. Continue. And then among all out neighbors of node 5, which is node 2, node 4, and node 6, you're going to update their shortest distance. For example, node 2, in the previous iteration, my shortest distance is 3, following the path S to 1 to 2, right? And you're going to compare the previous shortest distance, which is 33, versus the new distance, which is from S to the most recent added node, which is node 5, then from 5 to 2. 2 is here, which is 18. So you're going to compare 33 versus 29, and 29 wins. So you have to update. You're going to switch the shortest path to node 2 from S to 1 to 2 to S to 5 to 2. Okay, and do the same for node 4 and 6. And then again, the next step, fix a node. In other words, you're gonna find the shortest distance here, which is clearly node number 6. So you're gonna fix node number 6 here. And optimality test is t inside the node, continue. Again, updating the outer neighbors of 6, their temporary distance from 6, I can reach whom? I can reach 4 and t. So update 4 and t. For example, for again, in the previous iteration, the shortest distance is 41. In the new distance, I'm gonna go to 6 first. Wait, give me 1 second. I'm gonna go to 6 first, and then from 6 to 4. Go to 6, it's gonna cost me 16. And from 6 to 4, it's gonna cost me 20. So the total cost is gonna be 16 plus 20, which is 36. 1 minute. Which slide I'm talking about? It's here. Fixing a node. Okay, it's here. Okay, let me directly use the keyboard instead of the mouse. Oh my god, the mouse really cannot tolerate it. Can I use the keyboard here? Okay, sorry for the confusion here. So consider number 4, it is in the previous iteration it's 41. Here it's 30. It's 16 plus 20 equals to 36. So yes, you have to update the shortest path to be S to the most recent added node, which is S to 5 to 6, and then from this 6 to 4. And similar, how about t? Previous iteration, t is infinitive, the shortest distance. The new is 60. So of course, you're gonna make the 60. And again, you go from S to 5 to 6, then to t. Then you're gonna do what? Again, fixing a node. And among all these temporary nodes without a star, which one is the smallest distance, has the smallest distance? Node number 2, right? So you're gonna update node number 2. Sorry, so you're gonna fix node number 2. And in this node number 2, the Fn set here, t is still not inside. So continue. Go to step number 1, which means you're gonna update the outer neighbors of node number 2. So from node number 2, which node can you reach? You can reach node 4 and node t, and do the same here. Node 4, for example, the previous distance, shortest distance is 36. The new distance here is from S to 2 cost you 29, then 29 to 2 to 4 cost you 2. So the new distance is 31. 31 is smaller, so you have to update the distance, the path from S to 5 to 2 to 4 then. Okay, then do the same for t. Again, the next step is what? Fixing a node. And what you're gonna do is, okay, the smallest one is 31. So fix node number 4, 31. And t is not inside. T hasn't been fixed yet, so continue. So you're gonna find what is the shortest, what is the outer neighbors of node 4. Clearly you can see from 4 I can go to 3 or t, right? So you're gonna use the recursive formula again to update 3 and the t. And here's the result. And now you're gonna fix a node again, so 42 and the 47 only, so that you're gonna fix node 3. So node 3 is fixed, and then t is still not fixed, continue. From 3, which node can you go to? You can go to 2 and t, but I'm only gonna update a node which is temporary, which is not fixed. 2 is already fixed, so I will no longer update it anymore. So I'm gonna only update node t. And here, be careful, in the previous iteration, t is already 47. But in the new distance, I'm gonna get what? I'm gonna get from S to 3 first, which cost me 42, and then from 3 to t, which cost me 6. So the total cost here, the total distance here is in the new path is 48. And the 48 is greater than 47. So the previous path wins. So you're not gonna update this path. You're gonna keep it still the previous one, which is S to 5 to 2 to 4 to t. And now optimality, now not optimality, you still need one more thing. Now you're gonna update the temporary fix a node. And here your only candidate is t, so that you're gonna choose t. Okay, and then you're gonna do what? You're gonna do optimality test. Oh, t is inside. Okay, great, I'm done. So that's the shortest distance from S to t is 47, and the corresponding shortest path is S to 4 to 2 to 4, S to 5 to 2 to 4 to t, and that's it. Any questions? Clear? Okay, so after this lecture, please have a look at these examples. I would strongly recommend you do the iterations by your hand, by yourself, step by step. Don't just, for example, look at the iterations in the slides. You do it by yourself and look at the slides. They are very different, trust me. Okay, and in the next lecture, we're gonna kind of like summarize, have a look, I would say look back to the Dijkstra's algorithm again. I think it's gonna strengthen your understanding of this algorithm. Okay, and I think that is everything about today's class. Let me go back. Thank you very much for today's class, and see you next Monday. Have a good day and a good weekend. Bye-bye.